Okay. All rolls off incline falls to the floor, right? You got a free body diagram. You know what these forces are. Not gonna label, I'm not through this kind of test, I think of too much class time with this. We set up your order system like this. And find the projections of this vector onto the X and Y axes, and then you kind of cross the vector out and you analyze. Okay, normal force and this force have to add up to 0. This force would presumably be friction force, which opposes the component of the gravitational force down the incline. Okay, it's any indication that anybody on the test understood that. Again, not everybody's got that problem on the test. So I don't remember who did and who didn't. Okay. Well, then the ball goes to the floor. Because of this, you get an acceleration. And up that, find acceleration. Find the final velocity of the incline. Okay. Alternatively, other words by the net force. Which in this course is equal and opposite to the change in potential energy minus the work done by friction. Then you set that equal to kinetic energy. Now you should be able to do that either way if I specify it. If I give you the slope of the incline, you can find the angle. If I give you the angle, you can find the slope. So knowing slope and angle as you do if you know either one, you can figure out the change in potential energy. You know how far it will. Okay, so that's something that standard situation that based on the first experiment we did in the whole semester, you should understand by now. And of course, we spent a lab period talking about all that. Then you get down here. Now you have let's say V naught for the projectile equals VF on the ramp. Now you have a projectile motion. And you have equation of motion. Of course, for an ideal projectile, AY is G negative G. Okay. And AX is 0. So these equations simplify and use these equations to solve the projectile problem. And the open math is giving you numerous problems where you need to do that in one form or another. Now, depending on what question might have been asked, if they had a question based on the ramp, I might have given you how far it went and how far it fell. they ask you to calculate the final velocity on the ramp. Okay? Or the initial velocity of the projectile, same thing. And then maybe you have to go back and figure out something about the ramp. Okay? Told you how far it went on the ramp and said you like friction. Then you can figure out how far it went, whatever. So but these are the basics, and what I was expecting to see was an analysis based on these basic things. And I'm not sure I saw that on any paper. Okay. Although there were some that came closer than others. So I guess what I'm saying is, since we spent the better part of the class period talking about this situation and emphasizing the fact that this is the way you begin the analysis of a projectile, comes down to you want to take better notes and you want to review. Okay? And it really comes down to that. And what I'm not seeing across all my classes, I'm not seeing people following up on what they learn in class. Okay? Now, two reasons for that. One, the homework load is pretty heavy. I almost hate to expect anything more than just getting through all this homework, but the homework is a basis for putting things together, and class is designed to give you a broader perspective and help you put things together. So I'll be thinking about what I can do differently in the class, and I'm open to suggestions, okay? So really, my goal here is to help you be able to solve this problem, be able to understand these situations, and be able to apply the basic principles. Okay, so that's just one instance of something that was pretty strongly emphasized, especially this, and of course, free body diagrams. And I didn't see enough evidence of it on those whose tests included a problem of this nature. So the other things, and one that's really important for the stuff that we're working on right now is you got a beam, you got some distance from the center, you got the angular velocity, you get the speed at that point. It just requires that you know how far it is around a circle, because you got the angular velocity, you can figure out how long it takes you to get around the circle. Know how far it is around the circle and how long it takes, you can find out how fast. Okay? That's got to be intuitive. And we've done that a number of times, and somehow it doesn't seem to have taken in everybody's case. So you got to know that. And again, that comes down to drawing your own attention to it. Right? So when you suddenly see that, oh yeah, we get the kinetic energy of that domino on the beam. That's how you do it. Make yourself a note. Make sure you remember this. Okay. If you got to make a little bit of note, that okay, if you know how long it takes to do a revolution, and know the radius of the circle the thing that is moving on, then it's easy to calculate the speed. Then if a mass is running, you get kinetic energy. That turns out to be real important for some things we're going to talk about here in a little while. Very relevant to chapter 9. Okay. And in chapter 10. So there we have that. The other thing that I was talking about was what? What's the memory here? Oh, yes. U of X, you got X, you got 2 points here. You got X1, X2, U of X1, U of X2. What does U of X2 minus U of X1 tell you? It's the change in potential energy. Change in potential energy from X1 to X2. So if we go from here to here, what happens to our potential energy? Well, is U of X2 minus U of X1 positive or negative? Well, U of X2 minus U of X1 is the change in U as you go from here to here. I asked for U of X1 minus U of X2, be your change from here to here. Now, if you go from here to here, what's happening? If this is the part with the magnet, what happens between here and here? What happens down here on the tabletop? Well, it means you're going from position X1 to X2, right? And you have a negative potential energy change. You have a negative potential energy change. What's that do to your kinetic energy? Increases it by your energy change, your conservation of energy. If there's friction, well, then your loss of potential energy tends to increase your kinetic energy. But friction tends to oppose that. So you have not quite as much change in kinetic energy. You got to subtract the kinetic energy you would have if there's no friction. Well, you got to subtract the friction from that, right? Subtract the friction from the kinetic energy you have. There's no friction. Now, that all comes down to the work energy theorem. You're changing potential energy, you're changing kinetic energy, and work of the applied force. You've got to put all that together. Okay? So you got to know things like this. Now, this is going to be worth noticing. Okay, work done by the net force. This is work done by conservative forces, plus the work done by applied forces, right? Work done by conservative force is negative change in potential energy. And now, since W applied can be a little bit of a confusing idea, the work done by the conservative force is on the system. Okay? The applied force is applied on the system. So I put it on. The applied work acting on by the forces, the applied forces acting on the system. It's easy to get that back. And you got the change in kinetic energy. minus the applied work on the system equals 0. If you haven't pondered that a lot, then it's not likely to be there when you need it. Or you're likely to mess up. Actually, I kind of said that wrong. This doesn't make sense. Never mind, this makes sense. Okay. Had to make sense. Words made sense. It must have made sense, right? Does it make sense to me? Okay. Brain free. Okay. Spent a lot of time discussing this. Okay. Right there at the table in terms of the situation. Okay. Have the cart in the bag, talk about friction, talk about going up an incline, talk about a lot of the ins and outs. A lot of, video from lab. We can go Friday. You go last place. Okay. Okay, let's see if I can get this thing to focus. Okay. So, talking about a mass on a beam. And the question I posed is, mass pushing at the 25 centimeter position on this side of the beam, mass is on that side of the beam. We're assuming that the beam is massless, okay? So, force, well, this mass has to accelerate from 0 to whatever in a given time delta t. How much force does it take? Whatever the mass is times acceleration. Acceleration is Vf minus V naught over delta t. Multiply that by the mass. So it's very easy to get that. And started saying how far. It's a clumsy way to state it. So let's say through what distance. So exert through what displacement? Average velocity times delta t. Average velocity is average of initial final velocity, and acceleration is a change in velocity divided by time. So you have Vf squared minus V naught squared over 2 delta. So how much work? Well, now, what do we got to do to find the work? Okay, let's hope it follows me up here and focuses. Okay, how much work? It's force times displacement, assuming that implicitly that I'm always pushing perpendicular to that beam, and I'm always pushing in the direction of displacement, right? And also, I guess, if the mass is over here and I'm pushing on the opposite side of the beam, I'm not really pushing on the mass, am I? But I might as well be, because the force I exert here on this side is totally equivalent to force I exert at the same distance from the center on the other side. Okay, well, anyhow, how much work is F delta S equals, that's going to be this times this. Got the mass, F minus 3 naught over delta T. And then VF squared minus V naught squared over 2 delta T. And that's kind of a complicated expression. So we're not going to worry too much about that, be aware of it. But there's a calculation sequence you can do. You can easily calculate the force. You can easily calculate the delta S. And you can easily calculate the work, okay? Now, the point I'm trying to get to is, what if I don't exert that force at the 25 centimeter position? What if I exert that force at the 15 centimeter position? Or what if I exert that force at distance R? So what's the force at position R to do the same work? That force is going to have the same effect on the kinetic energy. Depends on the velocity of the mass. I'm going to state that as soon as obvious. If it does the same work, then the net work is going to be the same, and the change of kinetic energy is going to be the same. Okay, this is by the work energy term, which we need to understand in order to understand what I'm saying. I'm not going to work it all out because we're short in time, because we keep digressing to talk about what we need to do to get from the my lab materials to being able to solve problems without my lab materials. Okay, so anyhow, this is what we have. Turns out the force times R Okay, is always the same. We find this thing called torque, which is the force times R. Divided the force is perpendicular to the beam. And if I meant to do this up there, you know. Okay. The acceleration of the system, I have to define the system. So I'm trying to do this. Not enough board space. Okay. So here's going to be a picture. Going back to the beam, if I push closer to the center, then I've got to push harder to get the same result, because I have to push because the work I do is going to be through a smaller distance. Okay. If this mass accelerates from 0 to 20 centimeters per second, so in 2 seconds, then the force I have to exert at 25 centimeters is just the force I would have to exert on the mass of that washer, accelerated from 0 to 20 centimeters per second in 2 seconds. Okay, very easy to calculate that. If I want to push at the 5 centimeter position, well, that washer is going to have to go through the same distance in 2 seconds to get up to 20 centimeters per second to assume a uniform velocity. Okay. But I've only got 1/5 the distance to push it through now. Okay. Because my arc out here at 25 centimeters, it corresponds to this thing moving through whatever distance it takes to get up to 20 centimeters per second in 2 seconds. The distance we go out here is 5 times the distance we go here, because the radius of a 25 centimeter circle is 5 times the radius of a 5 centimeter circle. So any arc on the 25 centimeter circle is going to be correspond to 1/5 the arc on a smaller circle. Point is then that I need more force to do the same work in closer to the axis of rotation. So if I've got a beam I'll call this a light beam. Not talking about a light beam, we're talking about a beam of small mass, a light beam. We've got a mass here I don't want to use A. The distance F. And I've got a force exerted out here. The distance R. The beam rotates through angle delta theta. Then the force does the work F delta S, where S is how far this thing displaces along the arc. F is the steady state perpendicular to the beam, so I follow the beam around. My finger always remains perpendicular to the beam. So F does work F delta S. For delta S is R delta theta. Count that down, you're still right. Okay, so the work is F times R delta theta. And we'll call the F times R tau, which is the force. Acceleration angular acceleration. It turned out to be I'm skipping something here. That turned out to be tau times mr squared. Or I called you moment or another. And that's what we use. That's what it's on the slides. Should be mx squared. Mass times the square of the distance. If there are many masses, then your moment of inertia is the sum of your mass times square distance in the axis. And in every case, I wrote down here. What I wrote down wrong here. I started to write it out right. I gotta do that. Torque is I times alpha. Alpha is the angular acceleration. And you kind of want to keep that picture in mind as you work through the assignments.